Hello, and welcome to the AP Physics 5 stream. This week we're going to be talking about kinetic energy and the work energy theorem. My name's Jenny. I've taught physics for, I got to think about it, something like 12 years or so, and not all of it AP Physics, but I've taught both AP Physics B and AP Physics 1. And so I'm going to be your host for this stream. So let's go ahead and get started. Looks like there's not anybody here yet, but we'll go ahead and get started either way. And people can jump in when, pop in the chat and say hello when they arrive. Also, just so there'll be a replay as well, so people can check out the replay. Okay. So first, as always, just to remind you to follow Think Fiveable on all the usual social media channels, just so that you can find out more about events that are coming up. We've actually got a lot of new things coming up soon, so you should definitely follow along and keep an eye on all of that. So in this stream, we're going to talk about kinetic energy. We'll define it. We'll do a couple of quick examples, and then we'll shift and talk about work. Again, define it, talk about how it works. No pun intended. We'll look at an example with a pendulum, a pretty standard physics demo, and so it's one that you might have seen in your classes, and we'll kind of talk a little bit about how it works and how it can be used for different things, like in different ways than it's normally used. And then we'll just do a bunch of example problems, kind of, AP level free response type problems where we can look at how work and energy kind of go together and affect each other. So we can start with kinetic energy. So kinetic energy is a pretty simple one to define as forms of energy goes. Kinetic energy is simply the energy of motion. So anything that is moving has kinetic energy. The equation for kinetic energy is 1/2 mv squared. So it depends on the mass of the object that's moving and then the velocity squared. So like all forms of kinetic energy, kinetic energy is a scalar, which means it doesn't have a direction. And if you look at the equation, we see velocity in here, and velocity does have a direction. So you could have a positive velocity or a negative velocity, but once it's squared, that will go away. And so you will end up with a quantity that is just a scalar quantity. You have, I like to think of energy as like something that has an amount. You have an amount of energy as opposed to a velocity or something like that, which is got like a size and a direction to it. And also, like all forms of energy, kinetic energy can be measured in joules, and will almost always be measured in joules unless you're talking about, subatomic particles or something like that. So if we look at a couple of quick multiple choice type examples, we can start with an easy one. So which of the following has kinetic energy? A car parked on a hill, a car rolling down a hill, a piece of firewood before it is lit, and a piece of firewood as it is burning. So again, we don't have anybody here in the chat yet to answer, but the answer for this one would be B, the car that's rolling. Okay, so all the other things are not moving, and so they would not have kinetic energy. They would have other forms of energy, but not kinetic. Slightly more complex one. We have a ball thrown vertically upward, which is something we see a lot in physics. And it has an initial velocity v, and therefore it will have an initial kinetic energy k. So halfway to its maximum height, what are the velocity and kinetic energy of the ball? So if we remember from thinking about kinematics, if you have something that is moving vertically, its acceleration is always downward, right? Because it's experiencing the acceleration due to gravity. So the velocity will decrease at a linear rate until it gets to the very top, and then it will turn around and the velocity will increase at the same rate as it comes down. And so for the velocity, it's pretty easy. The velocity is going to just be half. So it's got to be either A or D. But if we remember the equation for kinetic energy, the kinetic energy does not go as the velocity, it goes as the velocity squared. So the correct answer should be D. It'll have half the velocity and 1 over the square root of 2 of the kinetic energy when it's halfway up. It will not have half the kinetic energy yet. Okay, so moving on, we can look at work. So work as a form of energy, because work is a form of energy, and it's a little bit trickier to define than kinetic energy. You can't just say it's the energy of this. It's more easily defined in terms of other forms of energy. So a good way to say it is that a force exerted on an object can change that object's kinetic energy. And this is referred to as work. Notice it says can change, does not always change the object's kinetic energy. And if we look at the equation, we can kind of see what some of the conditions are. So we have the change in energy is equal to work, which is equal to the force times displacement. So I know it's written as D, and displacement is usually written as delta X, but in this equation, the convention is to use D, but it is a displacement. And then we have a cosine theta in there, which we'll get to in just a second. So if you have a force that is exerted on something, but the object does not move because of that force, then no work is being done. Okay, you have to have a displacement involved in order to say that work is being done. And not all of the force will necessarily do work. Only the force that is parallel to the direction of the displacement. Okay, so again, we said you have to have a displacement, and only the force that is actually causing that displacement, or in some cases, working against that displacement. Like if something is slowing down, if you have something moving one way and the force is acting the other way, but parallel, that will still be doing work. It'll just be doing negative work. And how we see this in the equation is the cosine theta. So if you do the force times the distance times cosine of the angle between them, between the force and the displacement, that will tell you how much work is being done. Okay, so you're only taking the component that is parallel between F and D. Okay, so we're going to look at this pendulum demo. And so we're actually going to just watch this video. It's about 3.5 minutes or so. And this is a pretty famous demonstration, and I might kind of pause it and like highlight a couple of things as the demo goes on. So this is a section from a lecture by Dr. Walter Lewin at MIT. And again, when you see this, the demo might look familiar. You might have seen this in your physics classes, probably not to quite the same scale that they are capable of doing it in a big lecture hall at MIT, but you've probably seen something kind of similar. So let's go ahead and watch the video, and then we'll pause it a couple times and talk about things, but then we'll also talk about it a little bit more afterwards.
Now I want to return to the conservation of mechanical energy. I have here a pendulum. I have an object that weighs 15 kilograms, and I can lift it up 1 meter, which I have done now. That means I've done work. MGH is the work I have done, believe me. I've increased the potential energy of this object. 15 times 10 is about 150 joules. If I let it fall, then that will be converted to kinetic energy. If I would let it swing from 1 meter height, and you would be there and it would hit you, you'd be dead. 150 joules is enough to kill you. They use these devices, called a wrecker ball. They use them to demolish buildings. You lift up a very heavy object, even heavier than this, and then you let it go, you swing it, thereby converting gravitational potential energy into kinetic energy, and that way you can demolish a building. You just let it hit, and it breaks a building. And that's the whole idea of wrecking.
Oops. Oh, shoot. Okay. Sorry about that. I'm going to go back to that. We'll fast forward to it. Unfortunately, I can't really pause it too well because of the bar that comes up there. But what I wanted to point out, and if we can
now I want to
move it ahead to the right spot, right about here.
Kinetic energy.
Okay, here we go. What I wanted to point out here is that notice that when he lets it go from this height, which you'll see in just a sec, he gives it a little bit of a push. So this is significant. So we'll come back and talk about why it's significant in a second. And later he's going to do a variation on this demo, and he is most definitely not going to give it a push. So we'll talk about why and what's going on there. So I'll continue the video from here.
And that way you can demolish a building. You just let it hit, and it breaks a building. And that's the whole idea of wrecking. So you're using then the conversion of gravitational potential energy to kinetic energy. Now, I am such a strong believer of the conservation of mechanical energy that I am willing to put my life on the line. If I release that bob from a certain height, then that bob can never come back to a point where the height is any larger.
Okay, so I'm going to pause it for just a second there because he said something important. He said if he releases it from a certain height, then it can never come back to a higher height than that. And so this is conservation of energy, which if you're learning about energy in your classes, or if you already have covered energy in your classes, you know this is like something super, super fundamental. So the total amount of energy will be conserved. If you lift it up to a certain height, it has a certain amount of potential energy, and then you let it go and it starts swinging, but it cannot, if it's just swinging under the influence of gravity and nothing else is going on with it, then there's no way for it to gain more energy along the way. And so when it comes back up, it can't come to a higher height because it can't have more energy than it had before. But as we just saw with the one where he broke the glass, it did come up to a higher height than it did than before. It swung up high enough to actually break the glass on when it swung back. If he had just held it up there and dropped it, it would have come close to the glass, and it might have even touched it, but it would not probably have broken it. And I think you can see it even more strikingly the second time the thing swings by, where it comes up and you can see it kind of like the string hits the top of that little window and it like curves upwards a little bit. So you can see it's definitely coming up higher than it did when it started. Okay, it is reaching a higher height, which he just said it can't do. So I want you to think about that and think about the other thing that we've pointed out, and we'll kind of like lay it all out in a couple minutes. But just kind of keep that in mind as we watch the rest of this.
If I release it from this height and it swings, then when it reaches here, it could not be higher. There is a conversion from gravitational potential energy to kinetic energy back to gravitational potential energy, and it will come to a stop here. And when it swings back, it should not be able to reach any higher, provided that I do not give this object an initial speed when I stand here. I trust the conservation of mechanical energy for 100%. I may not trust myself. I'm going to release this object, and I hope I will be able to do it at 0 speed, so that when it comes back, it may touch my chin, but it may not crush my chin. I want you to be extremely quiet because this is no joke. If I don't succeed in giving it 0 speed, then this will be my last lecture. I will close my eyes. I don't want to see this. So please be very quiet. I almost didn't sleep all night. 3, 2, 1, 0. Physics works, and I'm still alive. See you Wednesday.
Okay, I love that little scream that you hear when it comes up to his chin. It's pretty delightful. Okay, so he talked a lot about making sure he didn't give it any speed when he let it go, or making sure he released it with 0 speed. And the reason for that is because what he really means is that he wants to release it with 0 kinetic energy. He wants the energy at that highest height to be entirely gravitational potential energy. Because if it is a combination of gravitational plus kinetic, if it does not have 0 speed when he lets it go, it's going to keep swinging, and it's going to still keep converting from kinetic to potential, but it's not going to just stop when it reaches the same initial conditions it had. It's going to keep going until that speed goes to 0. So the only other energy present is going to be gravitational potential. So it's going to have all gravitational potential, which means it's going to be at a higher height, which would obviously be dangerous because at that higher height, that's where his head is. So that would be a problem. So like I said, this is a pretty famous demo. I've done it not with a 15 kilogram, bowling ball or wrecking ball, but with a 1 kilogram weight because, I'm a wimp and I also didn't want to break the ceiling in the classroom. But it's commonly used to show a particular phenomenon. And I can't see, no. Okay, so the phenomenon that it's usually showing is conservation of energy. Okay, the whole point is that idea that it can't swing up higher than it started. That's the whole idea. But let's say, and I'm not saying we would want to do this, but let's say that you did want to actually make it hit it. Or let's say you were doing the earlier demo. It's probably a little bit less, violent. You're doing the earlier demo where you do want to swing it to a higher height so you can show that it's going to break the glass. We've seen that you need to give it a little bit of extra speed. So it has a little bit of extra kinetic energy. And the way you would do that is to give it a push. Or in a more physicsy way to say that, you would apply a force to it. And it's going to be in contact with your hands for some small distance while you're pushing it. So you're going to be applying a force, and the object is going to be displaced while that force is being applied. And then, therefore, thinking about what we just talked about on the last slide, you're going to be doing work on it. And you could maybe calculate that amount of work if you knew how hard you were pushing, or if you could estimate how hard you were pushing, how many newtons of force you were adding. And if you, made a video or something and, tracked how far it passed while your hands were in contact with it, you could calculate how much work that you did on it. And that amount of work measured in joules would be equal to the amount of kinetic energy it had in addition to its potential energy when it started swinging freely. And so from there, you could calculate how high it's actually going to come back up on the reverse swing. So if we want to see all this in kind of like diagram form, here's our pendulum at the beginning. And let's say we are going to give it a push. Okay, so a force is going to be applied to the pendulum at the top of its swing, in addition to the force of gravity, right? We're going to take that as a given. And so whatever mechanism it is that's letting it go, it is going to give it a little bit of a push. So that way, when it starts swinging, it has not only potential energy, but it also has kinetic energy because it has a speed. And so work would be force times distance or displacement. And I didn't put the cosine theta in here, and I tried to draw it properly, but we're going to assume that the force is in the same direction as the velocity. So the angle between them would be 0. And the cosine of 0 is just 1. So that cosine theta term is just like force times displacement times 1. So we don't really need to show it. So the pendulum moves while the force is applied, and you end up with additional kinetic energy equal to the amount of work, right? Work equals the change in energy at the top of the swing. Then it swings down to its lowest point. At that point, the energy is all kinetic. And it's also moving faster than it would have been if it was released from rest, right? Because it has more kinetic energy than it would have if it started with just all potential energy. So it's got a faster speed at the bottom than it would have if you just dropped it. And then finally, it's going to keep swinging upward until all of that kinetic energy is exhausted, until it's all converted into gravitational potential energy. And that gravitational potential energy is going to be equal to the gravitational potential energy plus the kinetic energy that it had over here. Also perfectly correct to say it's going to be equal to the gravitational potential energy plus the work done on it over here. And then at this point, both of those would be equal to the gravitational potential energy, and it's going to be at a higher height than where it started. And hopefully you wouldn't be doing the version of the demo with somebody's head there at that point. Okay, let's look at another couple of quick multiple choice style questions. So we have a hockey puck sliding across a horizontal, low friction, icy surface. So which force or forces do or does work on the puck? It's kind of awkward phrasing, but so if we look at all these forces, these would all be forces that would be acting on this hockey puck. So we have the weight of the hockey puck. Sure, that makes sense. We have a normal force, right? It's on a surface, so it's going to have a normal force pushing back up against the weight. It says low friction, but not frictionless, so there will be friction. And that's it. So we want to know which one or ones of those is going to do work, or maybe none of them will do work. So the correct answer here is C, friction. The weight is going to be acting on it, and the puck is sliding, so there is a displacement going on. But the key here is going to be that cosine theta, or that fact that only the component of the force that is parallel to the displacement is doing any work. Okay, and so we said this is a horizontal surface, and so the weight would be vertical. Normal force would also be vertical, and so neither of those would be doing any work. They would be perpendicular to the direction of displacement as opposed to parallel. And so the work done by both of those would be absolutely 0. The friction, however, is parallel to the displacement. It's in the opposite direction, so it would be at 180 degrees instead of 0 degrees, but it's still parallel. And so you would end up with negative work being done. The friction is not causing the displacement. The friction is opposing the displacement, but you would still have work being done. Okay, work can be negative. One thing to keep in mind, it's a little weird because we've talked about how energy is a scalar, and yet you can have a negative amount of work. So that seems kind of counterintuitive because work is also a scalar. But the reason why you can have a negative work is because it's, again, you got to kind of make sense of it in your own head, but I kind of think of it as it's a negative amount of work. Okay, in the same sense as with energy being a scalar, I kind of picture it more as something that you can have, right? It's not a substance, but it's kind of like that. You can have a certain amount of energy, you can transfer it to something else, you can change it from one form of an energy to something else. You know, it's not made of anything, but it's kind of acts more like a thing, more like you know, something like mass than it acts like something like acceleration or force or velocity. Okay, next question. We have a satellite of mass m, small m, orbiting a planet of mass large m in a circular orbit of radius r. Gravitational force between the planet and the satellite is Fg. So how much work is done on the satellite by the planet during one orbit? So if we look at our options, again, we want to think about force times displacement. So the tempting answer here is answer C, right? Because we know that in one orbit, it's going to go around the circumference of that circle. So it's going to travel 2 pi r, and it's going to be experiencing this gravitational force. So, you know, part of you might want to pick C, but the correct answer is actually A. And I guess we can think about this a couple ways. One of them is that there is no displacement. If it makes one complete orbit, then it came back to where it started. But more importantly, the gravitational force is acting as a centripetal force, right? So, you know, hopefully you have learned a bit about centripetal force, but what's always true is that it's directed towards the center of the circle. That's what centripetal means, center seeking. And so if the displacement, the direction of it is constantly changing, but it is always tangent to the radius and or to the, you know, to the circle, where the centripetal force, the direction of that is also always changing, but it is always acting towards the circle. So at any instant in time, the centripetal force and the displacement are perpendicular to each other. They're always at 90 degrees, no matter where you know, kind of freeze frame the motion of the satellite around the planet. And so, again, when you have forces that are perpendicular, that force is not doing any work. And so the correct answer would be A for that reason as well, that no work is being done. And this, you know, it's really more the second reason than it is the first one. I guess I should be careful about saying that, you know, if it comes back to where it started, the displacement is 0. That would be true for something like gravity. But if you have something like friction, you can still do work all the way around the circle, even if something comes back to where it started. So I know I've kind of gone back and forth between saying distance and displacement. And I don't mean to be like confusing here, but it kind of depends on the force. So if you have, you can have what's called a conservative force or a non-conservative force. And so it depends on if you have a conservative force, then it really does matter if it's a displacement or not. If it comes back to where it started, then the work done by it would be 0. And gravity would be an example of that type of force. If you have a non-conservative force, the path actually does matter. So you're looking more at distance in that case than displacement. Okay, got a little bit off track there. Sorry. The point that question was really trying to make, and the one before it, was thinking about the direction of forces and distances or displacements and the work done on an object by a given force. And this is the part that is really important, whether it's a conservative force or a non-conservative force. Only the force or the component of the force that is parallel to the direction of the motion does any work. And so it wouldn't matter in that case. In the case of a centripetal force, it wouldn't matter if it was a conservative force like gravity, or a non-conservative force like friction, it's still acting at 90 degrees, and so it's still never doing any work. So a centripetal force is a kind of very typical and very common example on the exam of a force that does not do work. So you might see it in a multiple choice question like that. You might see it as something, somewhere inside a free response question, whether you have to write about it or calculate something. A centripetal force never does any work, period. It also often applies to a normal force. So normal by definition is perpendicular to the surface. And so that often means that it's also perpendicular to the direction of motion, to the displacement. And so therefore it would also not be doing any work. That is not always true. There can be examples of normal forces doing work, but very often the normal force will not be doing any work either. But centripetal force is like always true. Centripetal force never does any work on the object that it is causing to move in a circle. Okay, so at this point, we're going to shift from the slides to bit paper so we can do a couple of free response style questions. So I'm going to close this stream, or this screen rather, and open up a different one. There we go. So we can look at a couple of more free response style instead of multiple choice style questions. So up here, I just have the equation for the work done for the work energy theorem, saying that the change in kinetic energy is equal to the work done is equal to FD cosine theta. And then we've got 3 different examples here to kind of work our way through in the second half of this stream. So I'm going to do my very best to draw acceptably on this screen. So, but we'll see. We'll try to make sure it looks, okay. All right. So we have the Pont des Arts Bridge in Paris is famous for the love locks that people attach to the bridge. So let's say that somebody dropped the lock as they were trying to attach it. We've got the lock's mass is 520 grams. The bridge is 6 meters above the Seine River, and the force of air resistance is 2.2% times the force of gravity. So we want to know how fast is the lock going when it hits the water. So if we did not have this thing here about air resistance, then it would be easier or easiest to solve this just using conservation of energy. Just saying the kinetic energy at the top of the bridge is equal to, the potential energy, gravitational potential energy at the top of the bridge is equal to the kinetic energy just as it hits the water. And then boom, done. But we have this pesky thing in here where the gravity is not the only force acting on this. So it is not true that the potential energy at the top is equal to the kinetic energy at the bottom. Some of that kinetic energy would be changed to heat, I guess, as the lock interacts with the air molecules on the way down. So it would heat up the air just a little bit as it passed through, probably heat up the lock just a little bit, some tiny, tiny fraction of a degree. And so it is not going quite as fast when it hits the water as it would if there was no air resistance. So for this, the easiest way to do it is to actually use the work energy theorem. So I'm going to draw our bridge. We'll just draw it as like a little H looking thing, and we'll draw the water down here. We'll make it blue because it's water. And then our lock is going to be dropped from the top of the bridge. So there's the lock. And we know that the lock is 6 meters up. And we know that its mass is 520 grams. This drawing is very slow. Which we can just, we know we're going to need to use kilograms. So I'm just going to say 5.52 kilograms. Just get that out of the way. And don't fall for the, small trick of units of measurement, measurement type conversions. Hopefully that's one you would spot. A 520 kilogram lock would be, that'd be a pretty heavy lock. I don't know who would be carrying that around on the bridge. All right, so now let's look at the forces that are acting on this lock. So we have the force of gravity. We'll call it Fg. And we have the force of air resistance. Probably should have drawn that one a little bit smaller, but that's okay. So I'm going to call this FAR. And what we know is that this is 2.2% or 0.022 times the force of gravity. There we go. So when you have these kinds of problems, there's sort of two ways to approach it. You can either find the work done by each force individually and then add them to find the net work done. Or you can find the net force and then use that to calculate the net work. In this case, I think I'm going to do that. I'm going to find the net force because it's just easier. I've got only two forces. They are parallel to each other. I don't have to do anything really with vectors here other than remember that I should be subtracting them because they're in opposite directions. So I'm just going to go ahead and find the net force. So F net is just going to be 1 Fg minus 0.022 Fg, and that's going to give me 0.978 times Fg. So almost the force of gravity, but not quite. And so then I can do work. Work is force times distance times the cosine of theta. So in this problem, it's going to fall straight down, and the net force is also acting straight down. And so they are completely parallel to each other. So I know that the angle is going to be 0, the cosine is just going to be 1, and so the work is really just going to be equal to the force times the distance it falls, or times the displacement. So switch colors again, just because we're doing a different step. So I'm going to say work. I don't even have to worry about the cosine theta. So work is going to be the force times the distance. And so that force is going to be 0.978 times the force of gravity, which we know force of gravity is just mg. So it's going to be okay. That is a terrible looking parenthesis. Let's try that again. Okay, 0.978 times mass times gravity. So this is 0.52 for the mass. And then acceleration due to gravity, 9.8. And when I multiply that all out, I get 4.98 newtons. And then times the distance, which is 6. And I get 29.88 joules. So that is the work done by gravity all the way from here to here. And so at the bottom, when it reaches the river, up here it had 0 kinetic energy. By the time it gets down to the bottom, I can say the change in kinetic energy is equal to the work that I just calculated. So that 29.88 joules, that's how much kinetic energy it has at the bottom. And so from there, I can just plug in the equation for kinetic energy to find out how fast it's going when it hits the water. So I don't know, we'll switch to this color. So I know that work equals the kinetic energy at the bottom, which is equal to 29.88 joules, which the equation for kinetic energy was 1/2 mv squared. So that's going to be 1/2 times the mass, which is our 0.52, times v squared. And so I already calculated this out ahead of time. But when you solve this, you end up with a velocity of 10.72 meters per second. So I know I'm skipping a little bit of algebra here, but it's fairly straightforward algebra. So 10.72 meters per second is how fast this lock is going just as it hits the water. All right, so that's one example of work being converted into kinetic energy. We can look at a second one here. And this one is also something that's happening along a straight line. So again, we won't really have to worry about the cosine theta, which we'll see when we actually get into the problem. But the third one that we'll do will have the angle piece in it as well. Okay, so in this one we have in 1979, Dr. Hans Liebold of Germany drove a race car 12.6 kilometers with an average speed of 404 kilometers per hour. And we're going to say, suppose he's driving that fast, then he applies the brakes to reduce his speed. And we want to know what was the speed if 3 megajoules of work was done by the brakes. So that prefix mega is not one we see a whole lot, but negative 3 megajoules of work were done by the brakes. And so we know the combined mass of the car and the driver is 1,000 kilograms. So notice that we have negative work being done here, which means that the direction of the displacement and the direction of the force are opposite to each other. That force is not acting to increase the kinetic energy, it's acting to decrease the kinetic energy. And so we should expect to get a final speed that is less than 404 kilometers per hour. And speaking of that 404 kilometers per hour, I think the first thing we need to do is to convert it into meters per second, because we're never going to use a speed like 404 kilometers per hour. So where did I do that? Sorry about that. Here it is. So 404 kilometers per hour. And I'm not going to show out the conversion on this. There is an earlier stream in the 5able AP Physics section that does go over dimensional analysis and all that fun stuff. So if you are not sure how this conversion would be done, then you can check that out. Also, you can't do this on the AP exam, obviously, but if you had a problem like this for your homework, I mean, I guess unless your teacher specifically tells you otherwise, it's generally okay to just Google this. So 404 kilometers per hour is 112 meters per second. So, okay. So we're going to say the work done here is the change in kinetic energy. So this is a little different from the lock because it doesn't start with 0 kinetic energy. It starts with some amount of kinetic energy. It's got a speed to start with. It's going 112 meters per second, which is pretty fast. And so we want to keep in mind that we're looking for the change in kinetic energy. So we're actually given the work to start, which is kind of nice. So we've got negative 3 megajoules. So megajoules would be times 10 to the positive 6. So I have 3 times 10 to the 6th joules, right? We want to work in joules. And that's going to be equal to the change in kinetic energy. In other words, it's going to be equal to the final kinetic energy minus the initial kinetic energy. So we could say 1/2 mv final squared. It's pretty messy, sorry. Minus 1/2 mv initial squared. Because we are assuming that this 1,000 kilograms combined mass of the car and driver is not going to change over the course of this. So the change in kinetic energy is due to a change in velocity. So 1/2 m times the final velocity squared minus 1/2 m times the initial velocity squared. So we know the initial velocity, that's our 112. We know the mass, that's 1,000. And so now we just need to plug all that in and solve for the final velocity. So 3 times 10 to the 6th is equal to 1/2 of 1,000 would just be 500 Vf squared minus 500 times 112 squared. Okay, and the squared goes inside the parentheses. I'm not squaring the 500, I'm just squaring the 112. And so if I do this out, that negative sign is just getting longer every time. Awesome. So 3 times 10 to the 6th equals 500 Vf squared minus, so when I do 112 squared times 500, I get 6.27 times 10 to the 6th. So if I add that to both sides, positive 6.27 times 10 to the 6th minus 3 times 10 to the 6th, I'll get 3.27 times 10 to the 6th. And then I will divide both sides by 500 and take the square root. And again, my handwriting is messy and slow, so I'm trying to just kind of talk through the algebra there and instead of actually writing it out. But in the end, if I solve all that for Vf, I get 80.9. Meters per second. Yeah. And just as a side note, because you are taking AP Physics, you are going to be taking the exam at some point. One thing to just kind of toss in as a time thing, if you are worried about time on the free response section and you get an equation to this point where all you got to do is a bit of algebra to solve for a single variable, and again, you're worried about time, this is a good point to leave it and go on to another problem, like especially if you've got ones that you haven't started yet and you're concerned that you're going to run out of time. And then come back for the algebra if you have time, because it's not an algebra exam, it's a physics exam. And so if you've done all the physics, if you've gotten to the equation, but you just have to do a bit of algebra to solve for one variable, that's worth like the least amount of points, just getting to this final answer. So you've already gotten most of the points that you're going to get. Come back and do the algebra at the end when you have time. If you have time to do all the algebra for every problem, awesome. But if you have to skip something, better to skip some algebra than to skip some physics. So side note, just on exam stuff there. All right, we've got one more problem, about 10 more minutes. I think we can do it, at least maybe kind of like an abbreviated version of it. So here we've got a box on a ramp, right? The classic AP Physics situation. So in this time, it's a block with a mass of 10-20 kilograms. It is sliding from rest down this ramp. The length of the ramp is 18 meters. And the angle of the ramp is 10 degrees. There we go. We are given that the coefficient of friction between the block and the ramp is 0.13. And we want to know how fast is the block going at the bottom of the ramp. So this is one where I actually think it would be better. I mean, you can kind of do this either way. Like I said in the last problem, you can find the net force and then find the work done by that force. Or you can find the work done by each individual force and then find the net work that way by just adding them. Because I did the first one way, I'm going to do this one the other way just to kind of show both. So in this case, I'm going to find the work done by each force. And then we'll add them all up at the end to find the net work done. And then that net work will be equal to the change in kinetic energy. Okay, so even on the exam, the equation you're going to see on your equation sheet is going to be delta E equals W equals FD cosine theta. But keep in mind, this is the net work. It is not just, it's the total amount of work. You can't just pick one random force and find the work done by that force. All right, so let's make a free body diagram so we can see what the different forces are. So we're going to have weight, Fg, going down. And at this point, you've probably done a million free body diagrams of boxes on ramps. So I feel like we can go through this pretty quickly. You'll have normal force coming up like this, perpendicular to the surface of the ramp. And then you'll have friction going backwards, and that is parallel to the direction of the ramp. FF. That's a terrible, terrible little F there. Okay, so there is no force pointed directly down the ramp. It's just the component of gravity that is pulling it down the ramp. And probably a good idea to just kind of draw those components in. So we will have a component that is parallel to the ramp, and we will have a component that is perpendicular to the ramp. And customarily, you'll be kind of thinking of this where the x-axis is parallel to the ramp and the y-axis is perpendicular to the ramp, instead of the x-axis being straight horizontal and the y-axis being straight vertical. Okay, so we're going to say x is parallel to the ramp, y is perpendicular to the ramp, which means I can label this guy, the parallel component, as FGX, and the perpendicular component as FGY. And this should be familiar by this point, right? You should have done plenty of problems with this general setup. So this angle will be 10 degrees, just like the angle of the ramp. And this angle will be 90 minus 10 degrees or 80 degrees. And it's useful to know both of those. Different students, different teachers kind of customarily use a different angle and the coordinating sine and cosine to find these components. I typically always taught my students to use this angle, because then the x component will be given by cosine and the y component will be given by sine, or force of gravity times the sine of that angle. I don't know, they and I just kind of always find it easier to just sort of mentally associate x and cosine, y and sine, like all the time. And so if you use this angle, the 80 degrees, that works. If you want to use the 10 degrees, then you just got to switch it, because now the x component is the opposite side instead of the adjacent side. And so it'll be FG times the sine of 10 will give you FGX. But you kind of conceptualize that in your head, whichever way works best for you. All right, so now I want to think about how much work is each of these different forces doing. So first of all, I can say that the normal force is doing no work at all, because it is acting perpendicular to the direction that the box is moving, or the block. The block is going to start at the top of the ramp. It's going to slide to the bottom, parallel to the ramp. And the normal force is going to be perpendicular all the way down. And so the normal force is not going to do any work at all. And so I don't need to worry about it at the moment. Same thing goes for the y component of gravity. It's not going to do any work because it is perpendicular to the direction that the block is moving. FGX will do work. It will do positive work because it is moving in the same direction as the block. The frictional force will do negative work because it is moving the opposite direction of the block. And if this block was moving at constant velocity all the way down, meaning that the kinetic energy was not changing, then we could say that the work done by this guy, the FGX, is equal to the work done by FF, and there would be no net work done, meaning the kinetic energy would not change. The block could slide right along with a constant velocity. But that's not the case here. We know that it is starting from rest and it is sliding down. So therefore, that's enough of a clue to tell us that there's no constant velocity going on here. It's starting from 0 and speeding up as it slides down. So I didn't really draw these to scale very well, but the FGX must therefore be bigger than the frictional force. And it is going to do more work. So the positive work is going to be greater than the negative work, and there is going to be a net amount of work done as the block slides down the ramp. So I'm going to start by looking at the work done by FGX. But actually, I can really think of this as the work done by gravity, because I've got the consideration of the angle already in this equation, and I don't need to do it twice. That, I think, is something that could maybe trip people up. If you're looking at this diagram and realizing that only FGX does work, I can see a trap where you would kind of use FGX as the force in this equation, but then still do the cosine of 80 degrees, and then end up doing the cosine twice. So you want to avoid that. So you can conceptualize it a couple different ways. You can either say FD cosine theta. F will be, work done is going to be FD cosine theta. So the F might just be FG, not FGX or FGY. The distance will be the distance it slides down the ramp, which is 18. And the cosine theta will be the angle between this force and the distance that it slides down the ramp, which is our 80 degrees. So cosine 80. Or you can conceptualize it as my force is this one, FGX, which is equal to FG cosine 80. And the angle between FGX and the displacement is 0. And so you'll still get the cosine 80. It'll still be the exact same thing mathematically, but you're just kind of thinking about it a different way. whatever way works best in your head, go for it. Either way, you'll plug in the same numbers. So for the force, we will have mass times gravity. So we'll have 1020 times 9.8 times, whoops, not times the cosine yet, sorry, times the displacement, or the distance it slides down the ramp, which is our 18. Now times cosine of 80. And when you multiply all of that out, you get 31,244 joules. So this is one of these things that you see with energy, is that a joule is not very big. Even though, as we saw in the video, 150 joules is enough to kill you. But unlike with newtons, where you typically end up with kind of fairly small numbers, or at least maybe in the hundreds or something like that, depending on what situation you're talking about, with joules, you very often get numbers in like the tens of thousands. So this thing has a lot of energy as it's sliding down. So that's the work done by gravity. We know that the normal force isn't doing any work. We now need to look at the work done by friction. And I know we're over time, but I think it's probably in our best interest to finish the problem. So I'm going to go through and finish it, and then we'll stop the stream at the end of this problem. But so in order to find the work done by friction, we need to find the force of friction, which is going to be kind of a multi-step thing here, because as we know, friction is equal to mu times the normal force, right? And so unfortunately, even though the normal force is not doing any work, we still need to find out what the normal force is, because we need to know because we need it to find the frictional force. So the normal force is going to be equal to this, okay, the y component of gravity. So therefore, it's going to be Fg times the sine of 80 degrees. So I'm going to plug in all of that at once. So I've got my coefficient of friction, 0.13. And then my normal force, which is y component of gravity. So I've got the force of gravity, which is mass times the acceleration due to gravity, 9.8. And now times the sine of 80. Oops, sine. There we go. Sine of 80. Okay, so if I multiply all of that out, I get, where am I? I get 9,844 newtons. So if I want to find the work done by that, work is going to be equal to F times D times the cosine of theta. And in this case, the theta is 180 degrees, right? The angle between the force of friction and the displacement of the box is 180 degrees. So the cosine of that is just -1. So I know that I can just multiply this force times 18, and then just remember to stick a negative sign in front of it. So I've got 9844 times 18. And I know that it's going to be negative. And so I end up with negative 23,035. joules. So the net work done will be the difference between these two, or 31,244 minus 23,035. Or I can say the sum of these two because the minus is right there because this is a negative number. So if I subtract those, I get 8,209. So that is the net work. And that is equal to the change in kinetic energy. And because it started from rest, that just means it's equal to the amount of kinetic energy it has down there at the bottom. And I know kinetic energy is 1/2 mv squared. So I can say at the bottom of the ramp, it has 8,209 joules of kinetic energy. So 1/2 times 1020 times v squared. And if I do out all that algebra, V comes out to be 4.01. meters per second. Okay, so that is it. We are a few minutes over time, so I am just going to sign off here. Again, remember to follow Think Fiveable so you can find out what's going on with new streams and all different AP subjects. And also, as I mentioned, some other new stuff coming up soon, which I think hopefully you'll really like. And that's it for tonight. Thanks.